Here we are in part two of the linear amplifier expose, I guess we'll call it. And you know, this was just a little project to pep up our little quarter-watt, AM transmitter. And it turned into kind of a linear amplifier tutorial, I guess. And a lot of it was relearning stuff for me. I haven't looked at this stuff for many years. So yes, we're going to go inside the box and go through the actual construction and the circuit and the schematic in detail. But let's talk about some simple concepts that maybe we skipped in the first video. First of all, when you think about audio amplifiers and you think about RF amplifiers, we use the term linear amplifiers. And both of those conditions require linearity. In other words, reproducing the input as perfectly as possible at the output. Certainly an audio amplifier has to amplify sounds as perfectly as possible, delivering them to the speaker. And we're trying to take a fully modulated signal, like an AM signal, and amplify it without distortion to send it to the antenna. It's a similar idea. And the tubes are working in a similar way to reproduce the envelope of the modulated wave perfectly. But when we say Class B or Class AB with audio amplifiers, we're almost always talking about complementary symmetry or push-pull style amplifiers. That is true with RF amplifiers. There are certainly push-pull styles of RF amplifiers that operate in the same way. But you have the added advantage with an RF linear amplifier that you do not have with an audio amplifier. That is the tune circuit, the magic tune circuit at the output. It can do some things that are simply amazing. When you bias a stage just on in Class AB, or not even on, Class B, where it's actually at 0 volts and the signal brings it above ground, you're only amplifying half of the waveform. The tube can only conduct in one direction. It can only amplify in one direction unless you're in the middle of the load line, as with Class A. So I'll put some diagrams up here and show you what Class A looks like. Class A is completely linear. You're operating within the load line and you get a complete amplification of the signal with no distortion. Small signal in, big signal out. Now with a Class B version of a single-ended amplifier, you're only able to amplify, let's say, the top part of the waveform, the part that with a solid-state device turns it on, or the part with the tube type that allows the grid current to flow and for the plate current to flow. And where do you get the other side of the wave? Isn't that going to be complete distortion? Well, the magic of the tune circuit actually mirrors the upward swing, and you end up mirroring that, and you end up with the complete waveform in the output, even though you're only amplifying half of it. So that technique is not something that's done with audio amplification, but it's done with RF amplifiers all the time. And this linear amplifier does just that. We're biasing it slightly on so that we're amplifying half of the signal, and then the tune circuit in the output makes the other half of the signal. Therefore, you get a perfect copy of the signal. So that's pretty tricky. The other thing we didn't talk about was grounded grid versus the common cathode style amplifier. And this is also true for solid-state amplifiers. There's no difference. We have a lot of advantages with grounded grid. We have the lower input impedance. We have the ability to dispense with neutralization because we get a lot of isolation from plate to cathode compared to plate to grid. And we have the distortion advantages that we talked about. Okay, let's do a quick review before we get into some tube ratings. Now remember, with a Class A amplifier, we're amplifying the entire envelope and the entire waveform, all 360 degrees of the sine wave, if it were a sine wave. And we're biased to the center point of the load line, whether it's a tube or a Q point, as with a transistor. The overall efficiency is poor, but the gain is high, and the distortion is close to zero if you do it correctly. In a Class B or a zero bias type amplifier, we're exactly on the x-axis. We have a little bit better efficiency, and we have some amount of distortion, usually around the 180 area. In Class C, because we're only worried about putting pulses into the tune circuit, very, very quick pulses into the tune circuit to light it up, and we're below the x-axis, we're higher than 80% efficiency, and some of the even higher classes like E and so on do approach the high 90s. And we have large amounts of signal distortion because we're not worried about it. We're just trying to amplify the carrier. We're not worried about the modulation. In Class AB, which is where we're operating, we're somewhere between the x-axis and the center of the load line. We're better efficiency than Class A, but we're less efficiency than in Class B. And we have small amounts of distortion. So this is kind of an eye chart, but these are all of the very popular tubes that were used back in the day for single sideband grounded cathode Class AB linear amplifiers. So let's look at our friend the 6146, and we can see that it has a maximum DC plate current, depending on the type, between 110 and 115 milliamps. You might see this on your two-tube 6146 rig, where you typically dip the plate at no higher than 200 milliamps or 220 milliamps, something like that. We also have an output PEP of around 50 to 60, and we have an average plate dissipation of 25 watts. So let's just keep all of that in mind. The 6146 with a 25 watt plate dissipation and with a maximum signal output of 50 to 60 watts PEP. So let's look at a typical linear amplifier. Now this is an old timer. It's a Knight T175, and it's very cute because they put the grid bias control right on the front panel. Remember what I told you about having to adjust the linear amplifier for AM service as opposed to single sideband service? Could you imagine if you actually had to adjust the grid bias to get the best distortion characteristics for AM or for sideband by wiggling something called grid bias right on the front panel? I don't think too many operators are ready for something like this today. Here is the Knight T175 schematic, and this is something interesting to look at. It uses two of the modern sweep tubes, the 6JE6 tubes, and it has a 12AT7 with both sections in parallel, attempting to drive a high voltage relay. And we detect the RF coming in from your transmitter. We click the relay and it automatically switches the linear in line. As soon as you stop talking, it clicks back, and now you can receive through the closed relay contacts. We have a voltage doubler to make the high voltage for the tubes, and we steal a little bit of the voltage to run the relay where there's an operate standby switch. We're using another type of voltage doubler. This is a full wave and this is a half wave to develop the bias that's used to set the amplifier to Class AB, and we have a bias adjustment on the front panel so we can set the bias properly for for AM modulation, linear amplification, or single sideband linear amplification. So very nice, interesting looking schematic. We have a nice little detector here so we can peak the carrier output. The T175. Now, the tube that the T175 used was a typical horizontal deflection amplifier. It has very similar cousins, the 6LQ6 and so on. These tubes were capable of very high voltage operation, very rugged tubes, more rugged than the 6146 actually, capable of about 70 watts PEP output, and that would be equivalent to a 15 watt AM carrier if you don't want to cause distortion. So let's say we wanted to make a 100 watt AM linear amplifier. We wanted 100 watts of AM carrier, okay, for about 400 watts PEP. How many of these 6JE6 tubes would we need to do that? We would need 6 of them. That's why we don't like to linearly amplify AM. So here's the critique of the amplifier that occurred in 73 magazine, and an excerpt from October 1967. Linear AM operation is much more critical than sideband, but when the T175 is tuned up according to the instruction manual and the grid bias is properly adjusted, there is no distortion. Now they're saying here that they're able to do a power input of 120 watts AM linear. Well, that's nice. These are all really nice, but I'm here to tell you that you didn't get any more than 30 or 40 watts of carrier out of this amplifier, no matter what this says. Here's a little more modern amplifier. This is a Palomar. Here they've gone as far as to get rid of that front panel grid control, and they give you at least an AM sideband switch. So this apparently puts the linear amplifier in the proper settings for either AM or single sideband operation. And notice they now have an external power supply. So things are improving a little bit by this time. What we're finding with linear amplifiers is when we're in the AM mode, we have to really set the output thinking about the dissipation of the tube. That really is our ultimate limitation when you're amplifying AM in a linear amplifier. So because we know the 5763 only has about 15 watts of dissipation, we have to limit the dissipation to around 6 watts. And basically that means that we fool around with the amplifier's bias and with the screen voltage, and we make it happy to be able to handle that AM signal that you're driving it with without getting distortion at the output, especially in regard to upward modulation and flat topping, so on. So the 5763 amplifier that I started with was not a great success. I was only getting about 2 or 3 watts out, and I'm not sure that the distortion was acceptable. Now, for a carbon microphone modulated transmitter, I'm sure it sounded fine. But I did decide that in general I was going to go to a little bit larger tube to try to get a few more watts out. So let's go through this schematic very quickly. First of all, we know we're using the Brune type neutralization system on a simple tune circuit on the input. So we need to put some drive into the tube. This 10 ohm resistor is just a parasitic suppressor. The bias is set here with this potentiometer. You must have a choke at this point or the Brune neutralization doesn't work at all. So you at least need a decent choke at this point here so that you're able to get the negative feedback into the network. Standard parasitic choke in the plate, oversized resistor feeding the grid so that we can keep this point here around the 200 volt level. I'm using a 400 volt power supply, which is okay for a 5763, but you're starting to get to the maximum rating of the tube and beyond. 100 milliamp meter, probably could have gotten away with a 50 or 75 milliamp meter with the 5763. And I did use a standard pi output network. You can go as low as probably 300 microhenry chokes on 10 meters. You don't need 1 millihenry, but these are usually available fairly inexpensively. So let's go to the larger amp. Here's the 6146B. The 6146B has enough dissipation that you can run it a little bit harder. So you can run it up at the 15 to 17 watt dissipation level. And I found that I could get out, with my 400 volts, I could get out 5 watts. With the full voltage that we usually run these at, which is 750, I expect we'd be able to get out 8 or maybe even 10 watts for the carrier. The output power in PEP-AM is always 4 times the carrier if you want to stay linear. Now, the question to you is, do people actually run it like that? Or do they typically overdrive these tubes in AM linear operation, especially on 11 meters? I'm not going to go any further on that. So the 6146B, really a pair of them is not going to be putting out too much when you're using them in linear service for AM. I know with my Heathkit Marauder, which you guys have seen, they have an AM mode, and when you go into the AM mode, they limit you to 100 milliamps on the input power. So if you multiply 750 times 100 milliamps, that's 75 watts input power. And I know for a fact we only get about 25 or 30 watts out of AM with a pair of these. So it's a little harder. They're running it a little harder than what I'm suggesting. But again, in the Marauder, because it's a single sideband rig and they simply reinsert the carrier for AM, you don't have that extra sideband to transmit, and I think that's why they're getting away with it. They're literally running the tubes at their full dissipation, over 35 watts each, and of course they have a fan on them, so they're able to get out a little bit more than my conservative 16 watts that I would have thought. They're getting something more like 25 watts out in the Heathkit Marauder. But again, you take a severe restriction when you are linearly amplifying AM signals. So I've got the AM carrier net going in the background. As a chassis for the Linear, I didn't want to do anything fancy because I knew this was not going to be a permanent project. So I took a cover, surplus cover, I had a few of these, and I bent it up into a chassis shape that we can use for the Linear amplifier. I did that with a couple of C-clamps and a stiff steel rule, and you can just bend it up on your table. Doesn't have to be anything fancy, doesn't have to be anything perfect, but that will serve as our chassis. Low cost because it's junk. So some of you may already know that I'm a big promoter of neutralizing amplifiers, RF amplifiers. And the reason we do this, even with high frequency pentodes like the 6146 and the 5763 and 807 and so on, is because it's so easy to get feedback between the plate circuit and the grid circuit. And you form what is known as a tune plate, tune grid oscillator. And of course, in sets like the Heathkit DX40 and so on, there's many stories of crazy things happening because the transmitter is not neutralized properly. And of course, the single sideband transceivers of the 60s and 70s, there's a lot of folklore about changing out tubes and having to change the neutralization circuit so that it works better. So one thing I wanted to bring into this is the idea of safety, because we're connecting a small value capacitor from the plate circuit to the grid circuit. So we have high voltage on one side and usually a negative bias voltage on the other side. And there's a very good chance that you're going to stick a tuning tool in there that's not insulated, and you're going to cause a short to the chassis, and it's going to explode the power supply, and maybe give you a shock, and it's just a bad situation. So when you look at all of these capacitors, one thing that is true of all of them is that usually one side is connected to the adjustment screw or shaft. And that's usually where the problem begins, because you put a screwdriver on there and you short that somehow to the chassis, and there's a big explosion and it's a bad scene. So what I like to do with these neutralization caps, and this is just a best practices from safety standpoint, you put the part of the capacitor that is attached to the shaft or the head of the screw to the ground end. That is the grid end of the circuit. And you put the other side to the high voltage. Furthermore, you could use a small capacitor, high voltage capacitor, in series with the neutralization capacitor. And this connects to the plate, and then the neutralization capacitor attaches to the other side. This gives you kind of a double protection, because it keeps the high voltage from ever even getting to the trimmer. So that's why you'll see a lot of these adjustments will always have a fixed cap connected to the plate circuit, and that tends to isolate the neutralization cap from the high voltage. Is it fail-safe? No, it's not. This could break down, but it is better than just using the cap from plate to grid with no series capacitance. And of course, the higher the better on the rating of these caps. For instance, if you're using a 100 puff series cap here, you'd want one that would have 3 or 4 kilovolts of protection on. So on this neutralization cap, and I've mounted it such that I could enlarge the hole and put a rubber grommet on there. That'll prevent the tuning tool from touching the chassis. And as you can see, the capacitor, as you can see, is stood off on 2 standoffs. That is insulated from the capacitor. Now this side is the hot side. The other side is the side I'm going to connect to the grid, which connects to the adjustment screw. So there will be a capacitor from this side going over to the plate of the tube. So I'm going through the meter shunting process. This is a 1 milliamp meter, and I'm trying to turn it into a 100 milliamp meter. So that took a 5.6 ohm resistor plus, a couple feet of this number 28 wire, and it's close enough. I'll show you how it tracks. Okay, you can see what we have on the meter compared to the digital voltmeter. Let's go up a little bit. Up around 40. It's reading 40, a little above 40, and it's 44, so it's a little bit scotch, meaning it's reading a little bit low. Let's go up to 60. It's reading 66. Okay, yeah, it's reading low, so let's go up to 100. 113. So it's about 5 or 10 milliamps high compared to the reading. So if that's on 100, it's really 113, I guess. But that's close enough. If we wanted to make this better, I would add a few inches of wire to the number 28, but I'm not going to do that. It's close enough for me. Where is it? Around 50, 55. Okay, so it's 5 or 10 high. But that's how to shunt a meter. There's not much to it. Now, to use a power supply to shunt the meter, of course, you have to have a series resistor. I have a series resistor here. I believe this is a 270 ohm resistor. That's just to keep the current low enough that we can get into the 100 milliamp range on a 0 to 20 type volt power supply. So the 5763 beam power pentode is a 6 volt tube, and it draws quite a bit of current. More current than the 6CL6 or the 12BY7. So we'll bring up the power to 6 volts slowly, and we'll watch the current meter. Let's bring her up. And it's starting to... Okay, that's about 6 volts. Looks like the tube lit all right in there. You can see the tube lit up. Now that's a 12 volt fan running on 6 volts. Nice and quiet, but moving a lot of air. These fans can be very noisy when you run them at their rated voltage. But if you run them at half voltage and they still run, usually they're a lot quieter. Also, we have our changeover relay, which is 6 volts. And as you can see, the current goes up. So we're under 1.5 amps. It's about 1.25 amps for everything. That's lighting the filament, running the fan, and operating the changeover relay. Aim for at least a 2 amp 6 volt power supply to run this thing. So we have to stop this one here. We'll have one more video where we get into the bring up as well as the neutralization and the power out adjustments, bias adjustments, and so on. Hope you're enjoying this series on linear amplifiers.